So with relative extrema that we just looked at with the first derivative and second derivative tests, we didn't need to worry about endpoints at all, because with those relative extremes, it's all about what's happening kind of in the short run or like in the middle of the graph. When we get to this idea of absolute extremes, like what is the absolute maximum value that we're seeing and what's the absolute minimum value, what can happen is if we're on a closed interval, the endpoints could be an absolute maximum or minimum. So we just need to be careful about where our function is defined. And if it's an open interval, then we just need to pay attention to how infinity is at play while we're doing that. So f of c says output is an absolute minimum if that function value is smaller than every other possible f of x value for that interval. And then similar idea for the maximum, where that f of c or that y value is larger than or equal to absolutely any other maximum value or any other value on that function. So some examples here like these, because these have some good cases, like especially if we have these open circles coming through. So this is a piecewise function. So what we can do is read here, so there's an absolute maximum of 2 at x equals 0. So that's happening right here. So that's at the edge of this function. So that's coming from where this interval is beginning. That has this largest output value. And then what you can see is it looks like we go down to this minimum value, but it's an open circle. So since our lowest value is technically undefined, is what the open circle is showing us, we don't try to guess what's the next smallest value because we can't define, it's like infinitely close, so we can't actually write out that number. And instead what we do is we say there is no absolute minimum. So if your maximum or minimum value is coming from an open circle on the graph, it's not an absolute minimum or maximum. And this case here, where we have kind of this closed interval, and then we can see this maximum value, so that would be our largest value coming through here at 4, 4. And then minimum value would be down here at 2, 0. So that's a case where we would have both of them, one value coming from the middle of the graph, one coming from the edge of the interval. So what we're going to be doing here in order to find the absolute extrema, we need to keep in mind the interval that we're working on, so the beginning and end. So we're going to need to evaluate the coordinates that are coming through from the edges of the interval. And this is really a comparison of y values, like what's the largest y value and what's the smallest y value. So once we have these outsides of the interval, we have those values to compare. But then in terms of what's happening between those two values at the edge of the interval, we need to go and look for basically all of the relative extrema. So that work that we just did, we want to look for the relative minimums and maximums and see how those compare to these edge values from our interval. And then we'll have a case of an open interval as well here, and we'll talk about that when we get to it. All right, so our routine is we're going to find critical numbers. So we're going to find our critical values, and then we're going to evaluate each as a minimum or maximum. I'm going to be going with that second derivative test. You can do the first derivative if you particularly like it, but I'll be showing second derivative here. Evaluate our function at each endpoint, and then we're going to do a comparison of those values to see what's the absolute minimum, what's the absolute maximum. All right, so we're going to have 3 examples here. So let's start with this x cubed minus 3x squared on 0 to 4. And what we can even do is start with the endpoints just before we start taking derivatives and things. So these endpoints or these interval points, so one is coming from x equals 0. So we'd have 0. If we plug that into our function, that would just give us 0. If we plug in 4, let's see, 4 cubed minus 3 times 4 squared. I'm going to plug that in here. So that's a 16. All right, so we have our endpoints. We'll come back to those. But now it's the process that we just did of finding relative minimums and maximums. All right, so first thing I'm going to do is find critical values. So f prime of x is equal to 3x squared minus 6x. I want to see where this is equal to 0. Let's see, we have a common factor of 3x there, which will leave us with an x minus 2. So we're going to have x equals 0 and x equals positive 2. So I'm going to have two coordinates here. We're going to have x equals 0, x equals 2, and what we can do here, let's go ahead and check out with the second derivative. So f double prime of x is 6x minus 6. So let's see, if we take that second derivative of 0, that's going to be a negative 6. So with that being negative, that is concave down. So something like this, which is telling me that's giving us a maximum value. And then if we evaluate that second derivative at positive 2, let's see, that would be a 12 minus 6, that's a positive 6. So that's positive, so concave up. So I kind of want to just double check those that we're not getting kind of extraneous solutions, kind of like we saw with that last example where it flattened out. But with these, we're seeing minimum and maximum values. We just don't know if they are absolute minimum and maximum values. So let's see, x equals 0 we actually already have. So I don't need that one because we already have that as part of our group. And then 2, if we plug in 2, let's see, that'll be an 8 minus 12, so a negative 4. So these are the coordinates I want to look at. And now it's just a matter of finding what's the largest y value and largest x value. So 16 is our largest y value, so that's going to make that our absolute maximum. And 2 to negative 4, or sorry, 2, negative 4, that y value of negative 4 is our smallest y value. So that's going to be our absolute minimum. And let's go ahead and take a look at this on the graph. Now with our graph, it's a little tricky since we're restricted to this domain here of 0 to 4. We can still get a visual going for it. So x cubed minus 3x squared. And actually I can show you how in Desmos to restrict the graph. Let me change that a little bit. So if you type in your function like we did there, what you can do is go space and use brackets. So it's this kind of squiggly brackets that we use for set notation. So brackets, and then just put in the inequality. So like we're going from 0 to 4. So I'm going to do 0 less than or equal to x less than or equal to 4, and then close those brackets. And that helps with the visual here in terms of you don't have to see the rest of the graph. You can see literally the interval that we're looking at here. So let's see, there's our endpoint 0, 0. There's our endpoint 416. That 416 is definitely our absolute maximum. And then this 2, negative 4, that would be our absolute minimum. So we can get a visual for what's our largest and smallest values. All right. I just like to double check that matches up, that we got the 2 does link to a minimum value, so nothing got messed up there. All right. Let's go to this next one, our function x plus 1 over x. And let's see, our points that we're collecting, I'm just going to put this over here. So we can have x equals 1, which is going to be a 1 plus 1, so that's 2. And then an endpoint at 5. So 5, let's see, 5 plus a fifth. Let's see here. I'm going to go ahead and just write that as a decimal, so 5.2. All right, so we have those points coming from the ends of our graph because of our interval 1 to 5. Now let's go ahead and take the derivative. I'm going to rewrite the function so that that 1 over x is rewritten as x to the negative 1. So taking the derivative, we're going to have derivative of x is just 1, and then we're going to have minus x to the negative 2. And then I'm going to go ahead, can I put this to the side somewhere? I just want to take the second derivative for a moment while we're in derivative mode. Sorry, I'm going to put it at the bottom here. Just going to leave room so we can get those critical z-scores, but I want that second derivative, which would be, let's see, negative 1 times negative 2 is positive 2, x to the negative 3, so that's a 2 over x cubed. Okay, I just want to save that to kind of check out our second derivative test once we find our critical values. So we have 0 equals 1 minus x to the negative 2, so it's like 1 over x squared. Let's see, I'm going to go ahead and add that 1 over x squared to both sides. And with that, I'm going to multiply both sides by x squared, so that'll give us x squared equals 1. Take the square root of both sides, and x is going to be a plus or minus 1. So we can have positive 1, which we actually already have as a coordinate there. We could also have negative 1. However, let's take a look at our interval again. That's a good thing to refer back to. We didn't really have to worry. It didn't really come up in this scenario because that value of 2 is inside the interval. But notice here we get x equals negative 1, but that's outside of the interval that we're looking at. So we actually don't want to look at that point. So here we get two values. One is already a point coming from our endpoints. The other is outside the interval, so we don't want to use it. I could go ahead and quickly think about if we look at our second derivative of positive 1, that's a 2 over 1, which is positive. So that's concave up. So that's probably giving us our minimum value, which we'll quickly confirm by just comparing these two y values. That wasn't necessary really, but it's kind of nice to have it confirm itself in multiple places so you know you're on the right track. So 2 is less than 5.2, so that means this will be our absolute minimum. And this will be our absolute maximum. And that's it. So that one only had the endpoints. And let's go ahead and graph this. I can show you that restricted domain function again. So is this x plus 1 over x? And we were looking at this from 1 to 5. So if we look at this graph, it's just increasing over this whole interval. So our lowest point would be this left-hand side of 1, 2. Largest value would be this 5, 5.2. And that's it. All right, our last one here. So when it says an open interval, that means we don't have endpoints. So we're not going to have these points to start off with. Instead, we're just going to go right into looking at our critical values. So I'm going to start by taking the derivative here, which derivative of x cubed is 3x squared, and then derivative of negative 2x squared would be a negative 4x to the power of 1. And I'm going to go ahead and take that second derivative so I can kind of take a look at that later. So that's a 6x minus 4. All right, critical values. Let's see, we have a common factor of x there, so we're going to have a 3x minus 4. So solving that, we're going to have x equals 0, and 3x minus 4 equals 0, so add 4 to both sides, divide by 3, so x equals 4/3. So the points that we're getting out, I'll go ahead and write these down here. We have x coordinate of 0, x coordinate of 4/3. This is an open interval, so absolutely anything that shows up is good here. If we plug in x equals 0 into our original function, we're going to get 0 out. If I plug in 4/3, and I do want the coordinate here, and with that, I'm going to have the calculator help me with this. I don't want to do those fractions. All right, x cubed, so we're going to do 4/3 cubed, and minus 2 times 4/3 squared. And we get this negative 1.85. I'm going to go ahead and do this convert to fraction. It's not pretty, but I'll keep it that way in fraction form. Negative 32/27. So I think I've mentioned this before, and if I haven't, I apologize, but with fractions, this function's so nice in the Desmos calculator where you can plug in everything, and if that's in fraction form and there's no rounding, it'll give you the decimal answer, but this convert to fraction will always give you the reduced fraction. So, negative 32/27. And with that, what I'm seeing in terms of a comparison, so comparing those y values, the 0 is larger, so that would be an absolute maximum. And this would be an absolute minimum. As far as this is telling me, but I'm going to go ahead and take a look at our second derivative test here. So let's see. 0, 0, and 4/3, negative 32/27. So if I plug these into our second derivative, so if I plug in x equals 0, we're going to have 0 minus 4, so that's negative, so that's concave down. So we're seeing something like that. And let's see, for plugging in 4/3, again, I'm going to have the calculator help me out here. 6 times 4/3. And then minus 4 is positive. So, oops, sorry, my pen changed there. Positive, which means it's concave up. So, what this is telling me is that in terms of this graph, and we're graphing this absolutely everywhere so it never ends, what I'm going to be seeing in terms of a graph is concave down that switches to concave up. Something like this. So it's likely we're seeing this absolute maximum, I gotta stop saying absolute because we're proving that it's not absolute. We're seeing this maximum at 0, 0. We're seeing this minimum at 4/3, negative 32/27, but they're not absolute, they're just relative values, and that's what the critical values give us, are the relative numbers. So to know whether or not it's absolute, we need to take a look at this to see how is infinity coming into play when we have an open interval. When it's closed, we're really restricted in and don't need to worry about infinity, but with this one, because of how it goes, there's no absolute minimum or maximum. So no absolute extrema with this one. We have relative extrema, but no absolute. So cases where we could look at this and maybe we did have an absolute maximum would be if we had something that was like concave down and then up and then down or something like that. That would be a case where we have an absolute maximum, but basically the trend with infinity on the polynomial has to be the same on both sides. But to go from negative infinity to positive infinity, all of our y values are covered there. So I wanted to make sure we saw an example where no absolute extrema came up, Otherwise, it's a matter of looking at those endpoints and then seeing those relative extrema in between and then doing a comparison.